All right, spanning tree, chapter 3. Scaling networks class. This is version 6. There's a video right now for version 5.2 you can review if you want to see some different stuff, but basically this is what we need to know for this class. So we'll talk about how to create topologies that can have multiple connections but not have loops. Loops, bad. If you connect a network to itself, it's possible to get packets that never die, and they just spin around and bog up your network and create chaos. We actually did that once at one of the television stations because we had a wireless link between a local site and a transmitter site, and the wireless link was not smart enough to understand spanning tree. So basically we thought there were different VLANs going on, and when it got over there, the entire network slows down, like the whole shebang. And we spent the better part of a day troubleshooting Wi-Fi, looking at packet captures, trying to figure out where is all this traffic coming from before one of the broadcast engineers said, oh, you know, I saw that one of the cables was dangling loose in the room that's got the link to the transmitter, and so I plugged that back into where I thought it should go. So loops, bad, can cause you no end of grief. There's a couple of protocols that we will look at, PVST plus and rapid PVST, and how to configure them in a nutshell. So we like redundancy. However, if you have redundancy in a place like layer 2 Ethernet, not IP, but take a step down from that, you create a loop, which is bad. Ethernet doesn't know what to do when that starts to happen. It will just try its little, each device on the network will try its darndest to handle all the traffic you throw at it. Right? They're doing its job. And what that does is drags your network to a screaming halt. You can call those broadcast storms if there are there's a whole bunch of different types of broadcast packets that happen on a network. The most common one's probably like an ARP request, like who has 192.168.1.1. That can go out to everybody, and if that's in a loop, it goes out to everybody over and over and over and over. That's no good. A unicast frame, 1-to-1, right? I talk to you. Similarly, if it doesn't have a destination MAC in the table, it spams it out to all the ports, says, I don't know which MAC address is supposed to get this. Out it goes to everybody, and then again with the new drawings in these. We'll scale this one for them. I like that better. So it forwards it out to every, so switch 2 in our picture here forwards out that to everything on the network. And it loops and loops and loops and loops and loops. It's bad. So how do we fix that? We use an algorithm, which is just a step of actions we take to solve a problem, to make sure that in this case, there's only one logical path. To make sure that something like this between trunks 1, 2, and 3 never happens. The way we do that is we block one of those loops. So one of those trunks, we say, that one doesn't work anymore. Turn that one off. So when you set this up, you will assign roles to ports. The root port is the port closest to the root bridge. Designated ports are ports which aren't root, but are allowed to forward traffic to other one. And then alternate ports, or backup ports, are the ports that are currently not doing nothing. So if that Ghostbusters symbol there represents the port we're currently blocking. F1 on switch 2 and F1 on switch 1 are currently turned off to prevent that loop from happening. So they would be in an alternate state or in a backup state. You can also disable a port, so if you manually want to get involved with this, kind of take some of the fun out of it. The root bridge is where we start our calculations. And the way you figure that out is there is a bridge identifier number we use, and lower is better. It's like a golf score. So when we look at that, how do we make the decision as to which path is the best? Oftentimes, these will all be the same. You know, frequently, like if you've got 3 ports or 3 switches that are doing spanning tree, they're all gigabit switches, or they're all, if you have an awesome data center, 10 gigabit switches or 100 gigabit switches. Or if you're living in the 1920s, you have 10 megabit switches. But by summing up each of the port costs along the path, so you've got fast Ethernet on switch 1 to switch 2 to switch 3, you add up the costs of those links from whatever it is we're calling the root bridge. That's how we figure out what that path costs and whether or not we're going to leave that one up. If you show spanning tree, you can see the port and the internal root cost path back to whatever we designated as the root bridge. Does it make sense? We figure out how fast the links are, and based on that overall speed to get back to whatever the root is, we decide if we're going to use that or not. The root bridge's job is to figure out these port roles. So it's doing the thinking for this mesh setup we're creating. It says, you're going to be a designated port, and you're going to be an alternated port, and it makes those decisions for us. And it makes them based on that cost path back to the root bridge. So it wants to choose, like a golf score, the lowest path possible. It wants to choose the highest speed way to get where it is you're trying to go. When it's the other port, so you've got 2 connections on a switch, right? The other port will be set as alternate and won't send traffic, which is okay. We don't want it doing that. Ugh. Let me fix this one too. Those pictures just got huge on us. So here's yet another specification from our friends over at the IEEE, 8021D. We're going to exchange these bridge point data unit frames that have the following included in the data portion of an Ethernet frame. If you think back to the last time you popped open Wireshark and there was this list of frame properties in there, those fields define spanning tree. And if you have a device that doesn't understand that, you can get yourself into trouble. But hopefully you're only working with high quality Cisco equipment that completely understands what's going on in here. And in there it includes all of these various flags: the ID, the version, the message, the path cost, the bridge ID, the port ID, how old the message is, how long was the hello, how is the formatting set up. This process pops one of these every couple of seconds. Each switch knows about its own ID, the root ID, and the path to get from the switch in question back to the root. It knows about the system as a whole, and depending on that ID number, the lowest one is the winner. Bridge priority defaults to 32768, which is 2 to the power of 6, 8, 10. Includes the list of VLANs that are participating in there. which can get you into trouble. If you have a device that doesn't understand VLANs, again, you're back into trouble. And then since there's a default, when all of, so you got 3 switches, you plug them all in together. By default, everything's set up and everything's got the same bridge priority. If all of those are equal, since we know MAC addresses are unique, we use a MAC address to figure out which one becomes the root. So basically, it's kind of rolling a dice that first time, because MAC addresses are, for our intents and purposes, pretty close to random. When you buy a device, you don't know what the last part of its MAC address is going to be. So everybody thought this was kind of a good idea, and as a result, a bunch of different protocols popped up to get it done. So that core spanning tree concept, we figure out multiple paths on a network, we make sure that we don't have loops, and then based on something, we turn on and off ports for what we're doing. A bunch popped up. The old school 802.1d standard was the first, and people saw that it was a little pokey for what you want. Remember when the first time you ever turned on like a complicated packet tracer, all the little blinking lights were red, and you had to wait a while before all the little blinking lights turned to green? That process of network convergence. Well, with original STP, figuring out who's the root bridge and who's got the right bridge ID and who's the fastest switch to get to here and there and everywhere, creating all that stuff took a long time, which we don't love. So as time went on, Cisco, of course, rushed right out, embraced that protocol and extended it. Then the working group gets back together and says, well, why don't we make 802.1W, which is a little bit of an improvement. And Cisco says, no, we got an even better one. We'll call it, they came up with RSTP, Rapid Spanning Tree Protocol, and they're like, we've got an even more rapid protocol. And so how the tree calculations happen, you can have either all the VLANs we know about and calculate the trees for everything, which if you've got a bunch of trees takes longer, or you can have it on a per VLAN calculation, which is a way you can actually increase the efficiency of your network. If you can have a spanning tree per VLAN, you might not have to leave those redundant links just sitting idle. You can have VLAN 1 go down this link and VLAN 2 go down this link, which is a way to improve the quality of your links. Goodness, this one's just trashed. I wonder if I'm missing a font or something for these. Pardon our dust while we upgrade the curriculum. All right, so what's so awesome about PVST Plus? We're going to have an independent implementation for each VLAN on the network. So you have 3 VLANs, and you have 3 instances of this calculation going on, figuring out the best way to do it. I still managed to get that squished on top of it. Maybe I should put it on a separate slide. All right. STP and PVST Plus use states that are either blocking, so we're not passing traffic, listening to figure out what's going on, learning by calculating up what's going on the network, actually forwarding data, and then turned off. Each system has a unique BID for each VLAN. Again, the lower priorities decide who's going to be the root for which VLAN. But again, you can see the thing we lose if we've only got one calculation for the entire network is that you have these links that are just sitting there doing nothing, and we don't necessarily want that. Waste of money. Oops. What's that? Both of them. They are janky. Kids these days. So here's this actually almost deserves a slide unto itself. Here's the types we have, the various links. Remember, full duplex, right? Both talking and listening, point to point. A connection to a switch. A shared port, a shared link is in half duplex mode in case you happen to have legacy hubs. Less of a problem these days than when it first came out. RSTP figures out who's the root, who's the alternate, the backup port. Don't use link types in most cases. Nobody's using hubs these days. Designated ports make the most use of this link type parameter, and if it's set, they transition to point super quick. So here are the different, here are the different types of connections we could have. On this network, this is a root port. These are designated ports. This is an alternate port, and this is a root port between the two. So S1 is our root bridge. They span out from there. This alternate port for this VLAN at least is shut down, and data will travel over it. And then in theory, if this link right here falls down, this link comes online, this alternate port will spark up, and we'll be able to get to stuff on S3 even though our drawing doesn't have anything on S3. Starting to make sense? That one's okay. So, on a Catalyst 2960, which you may have some experience with, you can go in and configure your spanning tree bridge ID by just setting it. Spanning tree for VLAN 1, root primary. Alternately, you can use the priority value to set it, or you can say spanning tree VLAN 1 root secondary to verify the bridge priority on that switch. These are important sort of security considerations as well as configurations. Portfast and BPDU guard. Portfast quickly turns the port on from a blocking state. And we brushed over this last week. I hope I'm not confusing you guys with Cisco 1, but Portfast is also that thing that means it won't spend a bunch of time trying to figure out what's going on if it's part of a spanning tree or not. This is relevant in the really real world because it's the thing that will trip you up with computers trying to get DHCP addresses if it's not enabled. If your port is busy messing around trying to figure out if it's part of a spanning tree or not, and the computer attached to it comes up in 5 seconds because it's a modern computer and it doesn't take forever to boot, the port guard will still be up and the port will be down when you ask for an IP address. So you'll send up, the computer will boot up faster than the system can figure out what's going on, ask for a DHCP address, not get one because it's not on the network yet, because the switch is still trying to decide if it's part of a spanning tree or not. And now you're screwed. And now technicians are running out to workstations trying to figure out what's going on. So one of the things you should be configuring on switches in the really real world is the spanning tree portfast nonsense on just about every interface that is not connected to a switch, a router, sometimes a server, depending on the server, but almost everything that is not like networking equipment should have this turned on. That way it turns on, it knows it's not supposed to figure out if there's any spanning tree going on or whatever. BPDU guard turns off a switch if it starts getting spanning tree information from what it thought was supposed to be a computer. So there are some nasty hacks you can pull if you can pretend to be part of the spanning tree network as a computer, which you don't want. So one of the steps you can take is to enable BPD UGuard to make sure that if it starts getting that stuff, it will switch the port to an error disabled state, basically turning it off and preventing any further mischief from going on, or preventing you from accidentally making a loop in your network when you didn't intend to. Ryan, you look confused.
Yeah, a little bit. Trying to figure out BPD, what does that stand for?
Oh, Bridge Protocol Data Unit.
And the whole point of it is so that if it gets spanning tree information it's not supposed to, it shuts off.
So Jacob's computer is plugged into the switch port, and Jacob turns on his computer and gets an IP address and is humming along, and now Jacob's computer starts trying to send VLAN information to the switch. And the switch goes, you're up to no good over there.
It's not supposed to do that, and it shuts off.
Correct.
Okay, so basically just for the switch to know
That
if it gets any information from this port, or information from an IP address that's not supposed to be giving it.
port, it's Ethernet. But so, exactly right. So this is a security feature. You can get up to no good playing around with VLANs, and what you're when you configure BDP UGuard on a port, you're saying, whatever you do, this port is not supposed to be in the whole spanning tree mix. So you're getting it out of that list. I could have, you've heard me talk about this before. This used to be part of Cisco, I think, 2. And when I learned about it, I was like, man, I could have saved Tribune a ton of money if I had known this. So PVSD Plus can do load balancing. So if you've got multiple VLANs, which we did, and multiple redundant links, which we had, instead of leaving one sitting idle the entire time, if you set them up so that VLAN 10 has one bridge and VLAN 20 has a different, you can make your more efficient use of that network infrastructure by having the stuff for VLAN 20 go down this path and the stuff for VLAN 10 go down this path. Makes sense, huh? And I just didn't know that that was a thing. I know, especially if you have this was like tailor-made for our network because we had like sales over here and marketing over here, and they were different VLANs, and could have been way faster. So Cisco, of course, improved things. If you use rapid PVST, which should be fine if all your gear is Cisco and you don't have to worry about vendor incompatibilities, you can turn that on a per VLAN basis, which is the good thing, right? It lets us configure those sort of redundancies and balance load and stuff. Those are your commands. Tell it which mode, tell it what link type you're talking about. You can also clear the spanning tree detected protocols to get rid of all the stuff it heard about before that. And then when you go to look at it, if you take a look at the spanning tree info for VLAN 10, it's enabled, and there's the protocol it's using. So this is also a great way to give yourself extra headaches. So now you've complicated your network a little bit and made all these, what used to be sort of physical issues, become logical issues. Right now you've added this whole other layer of stuff that you have to worry about. So when you get into trouble, it's nice to have a drawing, and that's what they mean by analyze the spanning tree topology. So what's in there? One way is you can do that if you haven't shut this off, which is actually, we talk about shutting this off for good reason in the Cisco class, or security class, is to show CDP neighbors. CDP neighbors will tell you what the Cisco discovery protocol that's running by default on every Cisco device, on every port, what devices are where. So if you've got 3 switches, CDP will tell you, oh, there's a switch over here and a switch over here and a switch over there. Then you should know, because you documented all this, what the root bridge looked like. So now that you know where the neighbors are, now that you know what your route is, you should have an idea of it. Okay, I expect my packets to go from switch 1 to switch 2 to switch 3 and not to switch 4. to get where they're going. Then you can look at show spanning tree VLAN to verify what the ports are doing and who's that root bridge, and compare what's really happening versus what you thought was going to happen. And that is, in essence, what troubleshooting is. Making like your conception of reality line up with what actual reality looks like. Show commands are always your friends. Show spanning tree. If you don't specify anything, we'll just spit out a little quick rundown of what's going on. We'll show you the status of all VLANs that are defined on a switch. So it looks like that. And in this case, from their root bridge, they've set up multiple redundant paths, which means, if this fails down, it could bounce traffic the long ways around. It really does give you flexibility on your network. Oops. So sometimes your spanning tree fails. Not great. That either is if something you expect to be forwarding becomes blocking, that's bad, or if something you expect to be blocking starts forwarding. Basically, you've got two different failing conditions. Either it's working too good or it's not working enough. In a switched network, you can manually remove it. You can shut down whatever interface is giving you grief. You can physically remove a cable, which is how we wound up fixing our little spanning tree issue. Somebody unplugged the cable that wasn't supposed to be plugged in and put a sticker on it that said, "Do not plug this in." The problem is, so you've gone and you've manually fixed all that stuff. When you plug that thing back in, you're probably going to wind up where you were before. So you have to go back into your configurations and sit down and work out, what did I set up here that I wasn't supposed to set up here? Once you figure that out, fix that. Change the bridge. Maybe you've got something in a VLAN 10 that you thought was in VLAN 20 or whatever. So figure out what's going on with your network that's not supposed to be there. Plug it back in and then monitor it. Don't just go home for the weekend. Networking problems always happen on Fridays before a 3-day weekend. Have we seen these before? These beautiful stacked configuration switches? I think you can get up to 9 of them. These 3750s will pretend like they are one big giant switch if you connect them through that little port up there. Cheaper than buying like a big 6500 series or whatever their most current blade setup. You get one management address to manage the entire thing through. The naming convention, like keeping track of which gigabit Ethernet port you're configuring, starts to get a little messy. But you can have as many as 9 of them. You really have to kind of keep straight in your head. If I'm messing with gigabit Ethernet 6/0/1, what I'm supposed to be working with. But it does cut down on the amount of administrative nonsense you have to worry about. And also those stack-wise cables transfer data as fast as the backplane, allegedly. So you don't take a hit. You can add more switches to that one spanning tree without actually having to increase the size of the spanning tree, since whatever goes on in that backplane is treated as if it was on the same switch. You can add another physical device or another 24 or 48 ports or whatever without setting up more spanning tree hops, since it just all happens through the back of it. I have friends at IEEE recommend that the size of your spanning tree doesn't exceed 7 switches. So there's your logical limit for your network. That will let you exceed that by having that treated basically as one giant switch and not having to worry about all this spanning tree nonsense. So there's a very brief summary of what we just talked about there. Spanning tree, MAC address database, lives on layer 2. Don't think about Ethernet, don't think about IP addresses when dealing with this. It's strictly an Ethernet kind of deal. We're either blocking or not blocking ports on specific VLANs, if you're using one of the advanced protocols. Those frames go between switches. Legitimate way to hack things is to spoof them, so our friend BDPU guard prevents that. PBST plus is Cisco's fancy instance of that. One spanning tree per VLAN. That's probably the most important takeaway from this, is that that is out there. Because like totally just I was familiar with spanning tree. I didn't realize that they had done that on an individual VLAN basis, and how to figure that out would have been awesome. And then 3750s and other brands of Cisco gear will let you do that stacking and configuration stuff. And then spanning tree treats that stack as if it was one switch and it doesn't exceed your limit. So that's spanning tree. Who wants to try it now?